So in our first section over simplifying with Trig's identities, we just kind of looked at some basic techniques with our trig identities, and we're going to continue using the same identities and still kind of keeping those basic techniques in the back of our brains, but we're also going to be looking at a few more techniques or types of examples that we may see, and a lot of these have to deal with factoring. Now, when we're looking at factoring trig expressions, I think a really helpful technique is to kind of bring it back to what would I do if this was just a normal variable expression. So like here we have secant squared of theta minus 1, and they ask us to factor the expression. So off to the side, I'm just going to write, okay, if I had x squared minus 1, and it wasn't a trig expression, what would I do? So in this case, I notice that my x is being squared, I have a binomial, and also 1 is a perfect square. So that tells me that I can use my difference of squares, and we get x plus 1 times x minus 1, which means that in our trig example, it's going to work very similarly, but instead of writing an x, we're going to write a secant of theta. So we're going to have secant of theta minus 1, secant of theta plus 1. Inside my parentheses, I don't have anything else that I need to simplify. I completed the directions they asked me to do, so that's going to be my final answer. Alright, on our next one, we have 4 tangent squared of x plus tangent of x minus 3. Again, I have tangents in this expression, but it would work the same way as if I had an x. So I'm going to come off to the side and just work it out that way. I have a leading coefficient of 4. It is a quadratic, and it is a trinomial. So I'm going to use my factoring method of the AC method. So remember that we would do 4 times negative 3 gives us negative 12. So I'm looking for 2 things that multiply together to give us negative 12, that add together to give us a positive 1. Well, that would be a positive 4 and a negative 3. So then we use those 2 numbers to break apart our middle term, and then we factor by grouping. So we get 4x times x plus 1, a negative 3 times x plus 1. So finally we get x plus 1 times 4x minus 3. And again, remember that that's not my final answer, because instead of having stuff with just x's, we have things with tangents, and so we need to kind of translate what that would mean for our tangents. So instead of just x's, I'm going to substitute my tangents in. Again, we're going to check and see if anything simplifies. In this case, it doesn't, and so that's going to be my final answer. Alright, next up, again, we're looking, okay, do I have a greatest common factor? No, I don't have anything in common. I have 3 variables, or 3, expressions this time, so I can't use a difference of squares. And then, if we notice, we also couldn't use our other technique, because this would be similar to if I had something that looked like x squared minus y minus 3. Well, notice that because my variables are different, or in our case, because we have trig functions that are different, I'm not going to be able to factor it as it is. So what we're going to need to do is rewrite one of our trig functions as the other one, which we can do, because hopefully we notice that we have a cosecant squared x, and one of our trig Pythagorean identities has a cosecant squared, and it also has a cotangent. So if we look at that, remember that our identity is cotangent squared of theta plus 1 equals cosecant squared of theta. So I'm going to use that identity and substitute that in for my cosecant squared. So I'm going to put cotangent squared of x plus 1, and then the rest of it is going to stay the same. Then I just need to combine. So I still have a cotangent squared of x minus cotangent of x, but I have a plus 1 and a minus 3, so that's going to become minus 2. Again, this time now that they're all three the same, I can look at x squared minus x minus 2. So I'm looking at what two numbers multiply together to give me negative 2, that add together to give me a negative 1. Well, that's going to be a negative 2 and a positive 1. Again, converting back to my cotangents, that means that I'm going to have a cotangent of x minus 2 times cotangent of x plus 1. Again, those can't be reduced any further, so that's going to be my answer. Now, this time, hopefully we notice it's a tad bit different because if we're looking at our expression, I don't have a binomial. I don't have a trinomial this time, so we can't use like our AC method or anything like that. This time we do have a binomial, and I see a lot of squares there. So technically we could use our difference of squares formula. However, it might be a little bit easier. Hopefully we notice that we have a sine squared in both of those. And so hopefully we recall back to our factoring techniques. Remember, one of our biggest and most important techniques is to always look to see if we have a greatest common factor and to try and factor that out first. In this case, we do have a greatest common factor, and that greatest common factor is sine squared of x. And so we would be left with cosecant squared of x minus 1. Now, a big thing here is to check and make sure and see if we can simplify anything. And in this case, we will be able to simplify. So notice that on the inside of my parentheses, I have a cosecant squared of x minus 1. And hopefully we recall from our first lesson that that's not one of my Pythagorean identities. However, it looks really similar to one of my Pythagorean identities, and it's the Pythagorean identity that has cosecant and cotangent in it. So notice that if I move my 1 over using subtraction, now we have what we have in our parentheses. So I'm going to use that, and I'm going to substitute that in for my parentheses. So I get cotangent squared of x, which that in and of itself is pretty simplified. However, hopefully we recall that I said anytime we see a cotangent or a tangent, and I also have sines or cosines, usually we want to try and see if using our quotient identity would help us reduce. So in this case it is, because remember that cotangent is the reciprocal of tangent, so it is cosine divided by sine. And since it's cotangent squared, it'll be cosine squared divided by sine squared. Well, now notice that my sine squared is technically over 1 in the first part. I'm multiplying, so notice that we have a sign in the top and in the bottom of our two fractions. So those would reduce, and we will end up with just a cosine squared of x. And because that's as simple as it's going to get, that would be my final answer. So let's look at one last example. This one's going to be really similar to our last one. Again, I'm noticing that I have two different cosine squareds. So I'm going to go ahead and factor that out to the front. And then I would be left with 1 plus tangent squared of x. And again, hopefully because we can see that I have a squared and a 1 on the inside. This time this is one of my Pythagorean identities. So 1 plus tangent squared of x is going to give us secant squared of x, or theta. And so we can substitute in. So I get cosine squared of x times secant squared of x. And again, that's pretty simple, but I want to keep on simplifying as much as I can. And hopefully we can kind of tell already that this is going to get pretty simple. Because using my reciprocal identity, secant squared of x can actually be rewritten as 1 over cosine squared of x. And so now, since I'm multiplying, my first cosine is understood to be over 1, so I have a cosine squared in the top and the bottom. And so those are going to reduce out, and so we will just be left with 1 as our answer, which is as simple as it can basically get. So we started this one by factoring, and we ended up saying, okay, well that expression is actually equivalent to just 1.